All right, let's take a look at numbers 14, and we'll probably go up to 17, maybe 19 on this. Use sigma notation to write the sum. So again, all we're going to do is we're going to take our sigma. We're going to pick a variable, and I just generally stick with I. And what I want to do is this. I want to look at each of these terms and figure out what in them is exactly the same every single time. And what we see is a fraction. We see a 1 in the numerator. I see a 2 in the denominator. And we see a parenthesis. All right. So the first number that gets plugged in here is 1. And then the final number that gets plugged in is 20. And I'm going to put that I where I want those numbers to be put. So we get the sum from I equals 1 to 20 of 1 over 2I. And if you wanted to write that as just 1 over 2I without parentheses, that's perfect too. But I generally would put the parentheses in just because they're in each of these problems here. All right, 15, there are several different ways of writing number 15. So again, I'm going to go I equals. I might start with 1. I don't know. We might have to start with 2. We might have to start with 0. We'll see in just a second. And as far as a numerator, well, the fact is there's no like end to this. So we're plugging in everything from 1 or 0, wherever we start, to infinity. So when I look at what do we see? Well, we see fractions, so that's nice. We see numerators of 1, so we'll address that in just a second. When I first did this the first time, I just threw a 1 up there, and then I had to erase it when I realized something later on. I look at my denominators, 1, 3, 9, 27. And this list, and again, the more you're exposed to it, the more you will see it. This list is actually the powers of 3. 3 to the 0 is 1. 3 to the 1 is 9. 3 squared, I'm sorry, 3 to the 1 is 3. 3 squared is 9. And 3 cubed is 27. So my denominator is 3 to the I power. But I must begin at 0 in order to get that first denominator of 1. Now, why did my numerator have to change? Why did I say I put 1 and had to change it? I changed it because our first term is positive, our second term is negative, then we go to positive, then we go back to negative. And if you remember, we talked about this when we first saw these sequences, that alternating sign back and forth is going to be a power of -1. Because -1 to an odd number is going to be negative, -1 to an even number is going to be positive. Since my first term is positive, then it's sufficient for me just to put I there. Because again, anything to the 0 would be 1 over 3 to the 0, which would be 1, gives me 1. Okay. Let's move on to 16 and 17, determine whether the sequence is arithmetic. If it is, find the common difference. So if you remember, all we're going to do to determine if it's arithmetic is I take the second term, so 3, minus the first term, and we see what we get. Then I take the next term, third term minus the second term, and we see what we get. We take any term, subtract the term before it, and see if we get the same thing. You could also look here at the terms themselves and just say, hey, from 5 to 3, we take away 2. From 3 to 1, we take away 2. From 1 to -1, we take away 2. From -1 to -3, we take away 2. Either way is fine, but just make sure you're showing me that work. So this is arithmetic, and our common difference is that -2. So 17, I'm just going to do the same exact thing. I'm going to say 1 take away 0 gives me 1. That's the second term, take away the first. Then I'm going to do 3 take away 1. I get 2. And I'm going to stop right there and say it's not arithmetic. As soon as you show me that when you take away two different sets of terms, we get different differences, then it is not arithmetic. Again, up here, I could just say, hey, that's +1, that's +3, and then I could jump down to say it's not arithmetic. All right. Let's do 18 and 19, write the first 5 terms of the sequence. So in this first one, number 18, we are told the first term is 3, so that checks out. And then we're told there's a common difference of 4. That means from this term to the next term, it's going to go up by 4, and then up by 4, and up by 4, and so on and so forth. So we get 3 plus 4 is 7, plus 4 is 11, plus 4 is 15, plus 4 is 19. Now, 19 is a little difficult because we're given the 4th term and the 10th term. There are multiple ways of doing this, so if you have a method that works, that's great. I like to think of it as, remember, arithmetic sequences are linear. So I like to look at this as like an equation of a line. So 4 gives me 10, and 10 gives me 28. So to find our common difference, that's our slope. So I'm going to go y2 minus y1 over x2 minus x1. I get 18 over 6, and that's 3. So now what I do is I take our equation, an equals dn plus a0, and I plug in our 3. And then I'm going to plug in one of these points. I'm going to take the smallest one, 4 and 10. I plug 4 in for the n, 10 for the term. And then we solve for a0. So subtract 12. A0 equals -2. So our sequence is D, which is 3, n plus -2, which we write as -2. So that's our equation. So now let's write the first 5 terms. Let's plug in 1, plug in 2, plug in 3, 4, 5. If I plug in 1, 3 times 1 is 3, minus 2 is 1. Plug in 2, 3 times 2 is 6, minus 4 is 4. 6 minus 2, sorry, is 4. And again, our common difference is 3 right now. So if you want, just jump up by 3. So add 3 more, add 3 more, add 3 more, and we have our first 5 terms. All right, we'll continue in the next video.